Hello all, welcome to the Invisible Energy Mastering Radiation in Thermal CFD. So, we call it invisible not because radiation propagates via electromagnetic waves, but because it is often the invisible error in engineering simulations. Many engineers are comfortable with conduction and convection, but they neglect radiation because the math essentially is hard. Today, we are going to fix that. So, in our webinar 4 today, we are going to cover radiation fully. In our previous sessions, we covered conduction, we covered convection. We essentially tackle the only mode of heat transfer that requires no medium at all. So our goal today is to take you from the whiteboard to the command terminal. We will cover 4 distinct phases here. The physics, we will demystify the T power 4 law, understand why black paint doesn't always cool things. And then we'll move to the crisis, where we will apply this to critical engineering scenarios, specifically looking at the battery thermal runaway, where ignoring radiation can make you, improperly predict your safety predictions, wrong by a factor of at least 8. Then we'll move into the strategy itself. We'll understand what are the CFD modeling strategies which are going to help you choose between the fast P1 model and the precise FVDOM ray tracing model. Ultimately, we'll try the execution as well. We will end with implementation and quality assurance, showing you exactly which lines of code to change in OpenFOAM to get a stable, accurate result. By the end of this hour, you won't just know the equations, but you will also know how to use them to prevent catastrophic failures in high temperature designs. So just a short background about myself. My name is Siddhartha. I've done my master's in aerospace engineering. I have 4.5 plus years of experience. I've done a lot of combustion analysis pertaining to high-speed combustion devices and worked on developing thermal systems as well for the said combustor. My expertise primarily relies on OpenFOAM. I've worked a lot with battery thermal, the system design, and IC engine simulations. My background primarily comes from technical training for CFD-driven product design. So we'll essentially talk about these 4 contents here today. We'll talk about the 3 modes of heat transfer. We'll cover the electromagnetic spectrum, the Planck's law in the radiation. Then with computational strategies, we'll cover how radiation power essentially is going to scale. We'll talk about the modeling strategies, then the implementation and quality assurance. Today, essentially, we'll cover from fundamentals, what is radiation, how do we tackle it, then computationally, how does it look like. So let's go down the first section here, essentially. The first sort of how your radiation is with respect to the 3 modes of heat transfer. We'll cover the electromagnetic spectrum, the Planck's law. We'll cover how radiation powers sort of scales exponentially, T to the power 4. And ultimately, we'll discuss emissivity and understand the myth of black paint. So to master thermal CFD, we first need to situate radiation among its peers. We have 3 distinct modes of moving energy, but they operate on fundamentally different rules. So on the left and the center, we have conduction and convection. These are linear processes. And idea is, if you double the temperature difference, you roughly double the heat transfer. Conduction essentially is the solid pathway. It relies on molecular collisions, the direct physical contact, and as the equation states here, you just have heat transfer is equal to negative K dt by dx. This is strictly limited by material properties, specifically thermal conductivity. Next, we have convection. Convection is essentially the fluid carrier. This requires bulk motion of a liquid or a gas. Think of this as physically hauling your heat away. The flow continuously replenishes cool fluid to the surface. It is driven entirely by flow motion. Now, radiation, essentially, this is the only mode that does not require any matter. It travels via electromagnetic waves and can cross a perfect vacuum. So looking at the equation here, we have epsilon times sigma, and in the brackets T to the power 4 minus T to the power 4 surroundings. Unlike linear behavior of conduction and convection, radiation scales to the 4th power of temperature. This exponential relationship means it behaves differently. So at high temperatures, it will behave vastly different from the other two modes of heat transfer here. Essentially, we want to understand, so for your simulation setup, what is the dominant sort of heat transfer mode in your situation. Conduction essentially needs contact, convection needs flow, but radiation, it needs nothing at all but line of sight. Now, coming to your electromagnetic spectrum itself, we are now leaving the world of molecular collisions, this is conduction, and fluid motion, this is convection. Thermal radiation is electromagnetic energy. It follows the same physics as light. This explains why radiation is the only mode that can propagate through vacuum. It doesn't need a medium to carry it. Now, looking at the graph here, the tall curve on the left, this represents the sun essentially at 5800, close to 5800 Kelvin here, which essentially peaks in the visible spectrum. This is the light that we see. However, almost all engineering problems, your batteries, your electronics, your engines, these happen in infrared. Now, at room temperature, objects are emitting light, but at a wavelength of roughly 9.7 microns. This is far too long for our eyes to actually detect. Now, notice how the curves on the graph shift to the left as they get taller. This is Wien's displacement law. Essentially, the peak wavelength is inversely proportional to the temperature. Now, as an object heats up, its peak emission shifts towards shorter wavelength. So at room temperature, you're going to be deep in infrared, 9.7 microns, but battery thermal runaway shifts to closer to 2.4 microns. It is getting closer to visible red spectrum. This is precisely why things essentially glow red hot, but vast majority of energy is still invisible. Now, this physics tells us exactly how thermal cameras work. A thermal camera is essentially an eye that is tuned to 9 microns, 9 to 14 microns here. It detects invisible peak shown on the bottom right here, and essentially reverse calculates the temperature based on the intensity. Now, looking at the equation here, the Planck's law essentially describes the shape of these curves. The key takeaway here isn't just the shift in wavelength, but the massive difference in the area under the curve. This is total power. So this area under the curve is essentially between room temperature line and the red hot line here. This essentially foreshadows the exponential power jump that we will discuss in the next slide. So as engineers, our intuition is often linear. We are used to conduction and convection. So in those modes, if you double the temperature difference, you roughly double the heat transfer. But radiation essentially breaks that particular rule. It doesn't grow linearly, it grows exponentially. So the governing equation that we saw previously, Q is equal to sigma times T to the power 4, that exponent of T to the power 4 is the most dangerous number here in thermal physics. So looking at the mathematics, if you simply double the temperature, you don't just get double the heat output, you get 16 times the power. So 2 to the power 4, 16. This is a massive escalation that essentially catches many designs off guard. At room temperature, the red curve is pretty flat on the left bottom here. Radiation is pretty much negligible, which is why we often ignore it in standard electronics cooling. But as soon as we jump to a fire scenario, somewhere around 1000 Kelvin, we moved essentially from 300 to 1000. This is close to 3.33 factor increase, but radiated power increased approximately 95 times here. So this non-linearity is the physical reason why thermal runaway is so violent. Once a battery or a system crosses a certain temperature, it enters that vertical part of your red curve and it starts dumping energy faster than any linear cooling systems, your fans or liquid plates can actually do to remove it. So this is where safety systems essentially fail. Now, coming to reality of emissivity itself, first of all, we define emissivity as a ratio of ratio ranging from 0 to 1 essentially. Think of this as a efficiency rating for how well a surface can radiate heat compared to a perfect theoretical black body. Value of 0 essentially means it is a perfect mirror, there is no emission, and value of 1 means that it is perfectly emitting everything. So on the far left, we have polished aluminium. Now, aluminium has an intensity of 0.04. This is polished aluminium. It is terrible at releasing its own heat energy. It traps heat inside. On the far right, we have materials like concrete, we have paint, we have water. These have an emissivity of 0.9 or higher. They are extremely efficient at dumping heat into the environment. Now, here is the critical physics rule that links these concepts. It is the Kirchhoff's law. A good emitter is also a good absorber, meaning that if you have high emissivity, this implies high absorptivity. So the cube on the right doesn't just release heat well. If you shine a heat lamp on it, it will absorb 90% of that energy. Whereas if you have low emissivity, such as the cube on the left here, it will have high reflectivity because polished aluminium refuses to absorb or emit. It acts as a heat mirror. It essentially reflects roughly 96% of incoming radiation. Now, in real world, most engineering materials are gray bodies. They fall somewhere in the middle of this spectrum. The idea essentially is they are selective emitters. So if you want to shield a component from fire, you want low epsilon. If you want a battery pack to cool down naturally, you want a high epsilon. Now let's get into the myth of this visual trap, the myth of black paint. Now on the left, we can see the visible light spectrum. To the world our eyes essentially is evolved to see, the color is dictating energy absorption. Black color cube absorbs light and white color cube reflects it. This leads to a common intuition that black things get hot, white things stay cool. This is true for solar loading, sunlight, but this intuition fails completely for internal heat dissipation. Look at the image on the right here. This is thermal infrared spectrum, where electronics, battery packs essentially operate. Notice that the black and the white cubes look identical. They are glowing with exact same intensity. This proves that in the IR spectrum, visible color is irrelevant. Both black and white paints have an emissivity greater than 0.9. To a thermal camera or a heat transfer equation, white paint is essentially black. So rule of thumb essentially is surface finish matters much more than visible color. It is not the pigment that matters, but rather the material structure itself. Paints are generally non-metallic polymers or oxides. So as the table shows here, they are excellent emitters, where epsilon is greater than 0.9. Now compare this to a material like polished aluminium. We have epsilon of 0.05. Bare metal acts as a mirror, trapping heat inside. Applying any color of paint breaks that mirror effect and allows the surface to radiate heat efficiently. So the verdict on common error box is quite clear. Painting a heat sink black does not make it radiate significantly better than painting it white. Now, if you are designing a battery casing to reject heat, you don't need it to be black. You just need it to be non-metallic or coated, right? Anodization, power coating, or even a layer of dust, at least, will raise the emissivity significantly better compared to bare metal. Before we get into, let's say, the equations that radiations will go through, first we want to understand what is this metric of view factor, right? View factor is simply the fraction of radiation leaving surface 1 that actually hits your surface 2. Looking at diagram A here, there are two parallel plates which are close together. Almost everything leaving one hits the other. So the view factor is simply equal to 1 or nearly equal to 1. Now, looking at the diagram beneath it, we'll see that, if we angle them, much of the energy is going to escape into the void. The view factor drops to 0.5. In CFD, the geometric calculation is quite computationally expensive, but it is necessary for accuracy. Radiation is not a one-way street, especially in tight spaces like battery pack. Heat doesn't, just disappear into the universe. It also bounces back. So radiation doesn't just leave, it also interacts, so to speak. If a battery cell radiates heat to its canister and that canister heats up, or it is reflective, it radiates energy right back to the cell, which is re-radiation or a feedback loop, so to speak. So to prove why essentially this matters, let's look at some simulation results here of a 21700 cell inside a canister. Now we ran this scenario with 3 different physics settings. So model number 1, no radiation. We only calculated conduction. Result was 45 degrees Celsius. Model number 2 was simple radiation. We turned on radiation but used a very simplified model, like radiating to a fixed ambient temperature. The result shot up to 52 degrees Celsius. Now we are overestimating, but this is leading to over-designed cooling systems. Now finally, with model 3, we have fully coupled, we model the enclosure effects as well, the view factors, the feedback loop between cell and the can. The result was 48 degrees Celsius. So takeaway here is precision. Ignoring radiation introduced a prediction error, but using a dumbed down version of a radiation model essentially gave us the wrong answer. So in tight enclosures like battery packs, you must account for how components see each other. That 3 to 7 degrees Celsius difference essentially determines whether your thermal management system passes or fails your certification. So when do we decide how each mode essentially will dominate? Well, this chart essentially tells us the story here of how heat transfer changes as temperature rises. We are comparing conduction convection against radiation. So at 300 Kelvin, as we can see here, the radiation is only just about 5% of total heat loss. In standard electronics cooling, it is often safe to ignore it to save computational cost. Coming to 1000 Kelvin here, with let's say something like furnace or fire, we have hit the crossover point. This is 50-50 split. If you ignore radiation here, well, your simulation is effectively missing half the physics. And at temperatures greater than 1500, let's say, like your battery thermal runaway, this is critical regime for designing your battery safety. Radiation dominates at 90%. Convection, conduction are now minority players. If you try to model a battery fire using only conduction and convection, you are essentially neglecting 90% of the energy transfer. So how do we know when essentially to switch? We use something like the tipping point ratio here as the equation shown. This essentially compares the radiative heat flux to convective heat flux. The radiative heat flux on numerator, this scales with T to the power 4. The convective heat flux on the denominator scales linearly with convection temperature. Now, because the top part of fraction grows exponentially while bottom grows linearly, there is inevitably going to be a point where ratio shoots far above 1. This is when radiation takes over. The rule of thumb here is very simple. Dominance is quite situational. For normal operation, like cooling a laptop, you can often get away with linear physics, but for failure analysis containing a fire, radiation is essentially the only mode that matters. It is the engine that is driving the failure. So let's move on to the second chapter here. This is radiation in critical engineering scenarios. Now, let's walk through the life cycle of a battery failure using the scale on the left here. We start at very bottom, 100 to 200 degrees Celsius. This is standard overheating. At this stage, heat transfer is driven primarily by conduction through contact points. As we climb to 200 to 300 degrees Celsius, we enter the exothermic decomposition. The chemistry inside the cell begins to break down and release its own heat. Pressure builds up inside this particular casing, and as the temperature rises to above 600 degrees Celsius, the tipping point occurs especially there. So as the red section here indicates, we enter radiation dominant phase, violent decomposition. At these temperatures, the physics essentially changes. The failure becomes violent. We are no longer waiting for heat. through touching surfaces. The cell essentially is now broadcasting energy as electromagnetic waves. Now, to understand why this is catastrophic, let's look at the key insight. At typical fire temperature of 900 Kelvin, the radiated power density is massive. This is calculated here at 3.1. So this is calculated here. The radiated power is approximately 3.1 times 10 to the power 11 watt per meter square. Now, the consequence of this power density is speed. So energy flux is high enough to essentially influence the adjacent cells to get to their own ignition temperatures of 600 Kelvin in mere milliseconds, no less. So this explains why thermal runaway often looks like a rapid chain reaction rather than a slow spread, because radiation bridges the gap between cells almost instantly, sort of bypassing this thermal inertia of materials in between. So looking at the critical safety question of how much time essentially do you have, the setup is a standard propagation test. Let's say we have a trigger cell in thermal runaway at 900 Kelvin, and we are timing how long it takes for the neighboring cell to reach its own ignition temperature of 600 Kelvin. The bar number 1 essentially says if you run a basic simulation with only conduction, which is relying on heat moving through your tabs or air gaps, the model predicts that you have over 60 seconds. This suggests that you have plenty of time for emergency cooling. Now, if we add convection to our physics, essentially this says heat moves faster across the air gap. The time that you have is going to drop to 45 seconds. And again, this seemingly looks like a manageable amount of time for you to have emergency cooling happen. But if you were to model with the full physics, adding your radiation in the mix as well, timeline essentially collapses to 8 seconds. Now, why does time drop so drastically? So look at the heat flux comparison as well. Convection is moving at around 25,000 watt per meter squared, but at this temperature, radiation is dumping 95,000 watt per meter square across that gap. It is pumping energy 4 times faster than other models combined. So this brings us to the most important factor, so to speak, the factor of 8. If you neglect radiation in a thermal runaway simulation, you aren't just off by a few percent, but you are essentially underestimating the speed of failure propagation by nearly 800%. So you think you have a minute to stop the fire, but physics essentially gives you just 8 seconds. Now, just now we have defined the view factors as what sees what. Now let's take a look at what happens when those surfaces are locked, essentially inside a tight space, like a battery cell inside a canister. So in an open environment, radiation leaves and never really comes back. But inside a battery pack, we have enclosure effect. The heat doesn't just disappear, it bounces. So as the diagram shows, radiation leaves the cell, hits the canister, heats it up, and then radiates back to the cell, creating a sort of feedback loop here. Now, this thermal echo chamber keeps temperatures higher than expected. So to really understand why this matters for simulation accuracy here, let's look at battery canister. Well, we modeled a 21700 cell in the canister using the 3 different physics. So model number 1, no radiation. Model essentially predicted 45 degrees Celsius. Then model number 2, simple radiation, which gave us 52 degrees Celsius. And ultimately the full coupled, it gave us the 48 degrees Celsius. So the essential question here is a few degrees of temperature worth, the few degrees of temperature difference between a shitty model of P1 radiation versus a very good model of radiation, is the few degrees change actually worth the extra computational effort? Well, ignoring these enclosure effects essentially caused a 7 degrees Celsius prediction error. In battery design, 7 degrees margin is quite huge. That difference can essentially determine whether you pass or fail a UL certification test, or whether your thermal management system meets its warranty life. So lesson here is that in tight packaging, you cannot just toggle radiation on and walk away. You must also account for the geometry, the view factors. So view factors are important because reflected energy in small gaps significantly alters the thermal balance here. Now, coming to anisotropic effects, we have sort of covered this during our lecture on convection or conduction as well. Batteries, for the most part, are not solid blocks of metal. They are tightly wound rolls of electrodes and separators. This creates anisotropic sort of thermal properties, meaning heat travels differently depending on the direction. We can visualize this as two completely different systems existing inside the canister itself. You have your highway and your radiator. Looking at the highway, the first one here, the spiral path, this essentially follows the copper, the aluminum current collectors along the winding. In this direction, thermal conduction is extremely high, approximately 200 watt per meter Kelvin. This is comparable to pure aluminum. In normal operations, this is how we manage heat, pulling it out through tabs and bottom of your can. But looking at the walls themselves, the radiation or the radial direction, heat has to jump through layers of plastic separators, active material, etc. The conductivity essentially drops all the way to 0.3 watt per meter Kelvin. So in terms of conduction, this battery is acting like an insulator in this direction. So heat struggles to physically push through these layers. Now, here is where physics essentially flips, because while those layers block conduction, they act very differently during thermal runaway event. If internal separator ruptures and temperatures spike, we stop relying on conduction. Those concentric layers turn into massive surface area for emitting energy. So that is precisely why we identify this as the radiator. Radiation essentially bypasses the physical resistance of the layers and broadcasts energy radially through the structure via electromagnetic waves. So again, the key takeaway, the very structure that insulates against conduction creates a perfect surface for radial radiation during failure. So this is precisely why fire spreads sideways to neighboring cells very quickly, even though material properties would suggest that they should be thermally insulated. So now let's understand the design strategies for thermal control. We understand the fundamental tension in battery design itself and effectively designing for two different physical regimes simultaneously. On the left, we have normal operation from 0 to 60 degrees Celsius. Here, the enemy essentially is internal resistance, whereas on the right, we have fault tolerance, which is for greater than 600 degrees Celsius. Our enemy essentially here is the thermal runaway propagation. So for normal operations, in normal daily driving, radiation is essentially negligible. We rely fully on conduction to pull heat out of the cell and into the cooling plate. For this, we want bare aluminum or thermal paste. The goal is good contact. We want to minimize the thermal resistance so that heat flows freely. Now, at this stage, the surface finish doesn't really matter much. We just want pure conductivity, like raw conductivity. Now, on the right-hand side, what happens when a cell fails if temperatures jump beyond 600 degrees Celsius? Suddenly, conduction is too slow to actually matter. We are fighting radiation. Now that bare aluminum surface becomes a liability because, as we saw earlier, it has emissivity of only 0.05. It acts as a mirror, trapping the heat inside your particular pack. So to survive this, we need high epsilon, essentially high emissivity coatings like paints or sleeves, etc., to help the failed cell dump its energy, or at least we need reflective shielding to protect the neighbors. Now, critical trade-off here, bare aluminum is excellent for conduction, like cooling the car while driving, but it is terrible for emission, whereas adding a coating improves safety significantly, but that coating adds a tiny layer of thermal resistance that hurts normal cooling performance slightly. So you often have to sacrifice a tiny bit of normal cooling efficiency by adding coatings to gain massive safety margins during a crash or a failure situation. Okay, we do have one poll here. So your simulation shows a component heating up. If the temperature doubles, how much does the radiated power increase? This is the T to the power 4 The temperature doubles, how much does the radiated power increase? It is 16 times. Great. So 2 to the power 4, this is going to be equal to 16. Cool. Let's move forward with the computational modeling strategies. We'll try and understand how CFD can play a role in effectively, managing how to model your radiation. So to kick off this section, essentially, let's take a look at the rule of the thumb on the bottom. It says, don't use a cannon to kill a mosquito, but don't bring a knife to a gunpoint. Radiation modeling is computationally expensive. As analysts, the job essentially is to pick the right tool for the specific temperature regime that we are studying. So on the far left, the option 1, the simplest approach is ignore radiation completely because the temperature is less than 150 here, because this is standard for electronics cooling, like designing a laptop fan or a server rack, because at these temperatures radiation accounts for less than 5% of heat transfer. It is essentially safe to ignore or neglect it to save your simulation time. Option 2, this is the linearized model or the middle ground. Now, condition essentially is what happens when temperatures are between 300 to 600 Kelvin, like your industrial heating or your steady state engine warm-up. In these cases, we cheat physics slightly. We take the complexity to the power 4 behavior and force it into a linear coefficient. This is similar to how we handle convection. This essentially gives us decent accuracy without heavy computational penalty, provided that temperature differences are not too wide. And ultimately, we have option 3 here. This is full ray tracing. Now, what happens in a case of thermal runaway where temperatures are greater than 600? Well, in such cases, again, T to the power 4 nonlinearity is too violent for shortcuts. You cannot linearize a fire. You must solve the full RTE equation, the radiative transport equations, to capture how energy beams across gaps essentially reflect off these surfaces as well. This model is slow, but it is necessary for safety analysis. It is essentially the only way to be accurate. So if you are cooling a PCB, stay on the left. If you are containing a battery fire, move to the right. Using linear models for a fire event is like bringing a knife to a gunpoint. Coming to how do we choose the right model? Well, let's start at the very top here with the most basic question: is temperature greater than 400? If no, you are in the realm of standard electronics cooling. Radiation is likely contributing less than 5% of your heat transfer. The smartest engineering decision is to ignore radiation. It saves computational cost and barely affects your results in decimal points. If your answer is yes, temperature greater than 400, then radiation will matter. Now, we have decided how to model it. The question you should ask yourself is, essentially, if it is enclosed, if it is enclosed, if it is not enclosed, on the right hand side, there should be no. Then radiation is important. You can use, linear model, but use it carefully. But if it is enclosed and if it is, thermal runaway, then essentially you are sort of modeling, high amounts of radiation that are multiplying themselves. So for this particular case, you want to use the full nonlinear ray tracing. You cannot compromise on physics because lives are going to be at risk. So essentially, bottom line here is use simplified models for modest heating to save time, but use full fidelity ray tracing for safety analysis whenever you have temperatures greater than 400. There are a few key equations that I will just cover about because we have done a lot of theory, but when it comes to actual calculation, you don't need to memorize so many things. You only need these 4 things here. So these 4 equations essentially cover 90% of radiation challenges you will face in battery engineering. So equation number 1, this is theoretical ceiling, essentially the black body limit, essentially says the maximum possible energy an object can emit at a given temperature is given by this particular formula. The second equation, the real material, this is emissivity equals to epsilon times sigma times T to the power 4. This converts this theoretical maximum into an actual output because we learned that the myth of black paint This epsilon value is what distinguishes essentially shiny aluminum can from a wrapped battery cell. So you want to include your emissivity right here. Equation 3 is the heat transfer driver. This is the most practical equation for hand calculations or net exchange. So engineering is not just about what you are emitting, it's about what you lose to the environment. The driving force is difference between your temperature to the power 4 and the surroundings to the power 4. So this highlights why a hot battery in a hot box essentially cools very slowly, because the surrounding temperatures themselves are quite high, reducing the net heat exchange. And ultimately, the fourth equation, this is the CFD cheat code, so to speak. This corresponds to linearized path we looked at in the decision tree previously. So approximating the mathematics as heat radiation is approximated to 4 times epsilon times sigma t to the power 3. We can treat radiation just like convection. This is shortcut, essentially allows us to run fast, stable simulations for moderate temperature rises less than 150 without actually solving the expensive RT, 150 degrees Celsius. So now I want to cover how we can model radiation in open form. In open form, when you decide to simulate participating media like fire or smoke, you generally have 2 workhorse models. There is the P1 model and there is the FVDOM model. Think of this as a choice between floodlight and a laser essentially. So on the left, we have the P1 model. This is isotropic diffusion approximation. Instead of tracking individual rays of light, P1 essentially treats radiation intensity like gas diffusing through a room. It assumes that radiation is isotropic, meaning it pushes out equally in all directions. The biggest benefit we get is that it is incredibly fast. It collapses the complex physics into a single diffusion equation. And ultimately, this gives you very low computational cost itself. But because it assumes uniformity, it cannot handle directional beams or sharp shadows. It is best used for what we like to call optically thick media. Think of a dense soot-filled furnace where visibility is 0. When compared to FVDOM model, this is discrete ordinates method, finite volume discrete ordinates method. Essentially, this is ray tracing approach. It solves the radiative transfer equation, RTE, along specific discrete angular directions. The benefit is it captures the details. It can model shadowing, collimated beams essentially, and directional heat flux as well. It works for both clear air, this is optically thin, and dense smoke, optically thick. The biggest sort of letdown here is that it costs a lot. Computational cost is very high because solver has to calculate a transport equation for every single angle that you define. So decision again comes down to the balance that you want to sort of maintain here, balancing computational cost with physical accuracy. If you have a massive sort of soot-filled furnace where light bounces everywhere, we can use P1 model to save time. But if you have precise setup with clear sight lines and distinct heat sources like a battery fire, you need the accuracy of FVDOM. Again, let's reinforce this physics one more time. We are looking at heat flux versus temperature. We have conduction, convection, and radiation. The blue color line, the dashed one, is convection, conduction. It essentially grows linearly. This is what handles cooling in your laptop or car engine, etc. The orange solid line here, this is radiation. It starts very slow, but it creates this hockey stick curve. Once we cross 1000 Kelvin threshold here, it essentially goes vertical. Now, above 1000 Kelvin, radiation isn't just a factor. It is primarily the only factor that will matter for the most part. So to put a number on this, in combustion systems or furnaces or battery fires, radiation essentially accounts for 50 to 90% of total heat transfer. If you are simulating a fire and you leave out radiation, you are effectively deleting half or more of the energy inside your system. Now, here is sort of a shift in thinking. Previously, we spoke about solid surfaces radiating heat, but now we are talking about participating media. Now, in high temperature flows, the air itself is not clear. because it is full of soot, smoke, and combustion gases, so to speak. These particles absorb and emit energy sort of volumetrically. This means the fluid isn't just carrying heat via convection, but fluid itself is also glowing via radiation. So this makes CFD simulations quite difficult because of coupling, because radiation introduces massive source term into your energy equation. This alters the fluid temperature, which alters the density, which changes your buoyancy and the flow speeds, and the whole circle sort of keeps going there. Okay, so now we have arrived at the governing equation for everything we are discussing, the radiative transfer equation, RTE. Well, holistically, to look at it, this is integral differential equation, unlike the standard heat equation, which relies on local gradients, which is what is happening next to you. This equation essentially connects everything to everything else. It describes how a beam of radiation changes intensity as it travels along a path S. So let's take a look at this equation term by term. We'll just try and understand. So on the left side, we have change in intensity. So as we move a particular distance, we are going to get either brighter or dimmer. And on the right hand side, we have 4 different drivers. These are emission, absorption, outscattering, and the final term in-scattering. Emission essentially is a source term, which is fluid itself is hot and emits its own energy into the beam. So the hotter the fluid, the more energy it is going to add. The second term we have, this is absorption. This is a sink or a loss. So smoke or soot essentially absorbs some of the beam's energy. It is going to make it dimmer, and that's why we are using the negative sign here. Then we have outscattering. This is also a loss. The beam hits a particle and bounces off in a different direction. It leaves our particular path, hence the negative sign again. And ultimately, in scattering, this is the coupling term or gain, represents radiation traveling in other directions that hits a particle and scatters into our path. So integral symbol essentially makes mathematics very hard here, because we are coupling every direction to every other direction. So this essentially becomes this 7-headed monster, where this equation is quite famous for crashing your simulations. So we need 7 different dimensions simultaneously, which is 3 spatial coordinates, x, y, and z, then the angular coordinates, theta, and your phi, the wavelength, the lambda, and ultimately time t. With respect to the spatial coordinates, this tells you where you are. With respect to angular coordinates, this tells you in which way you are actually looking. And wavelength tells you the color of the heat ultimately, and time is time. Now, because a direct solution is computationally impossible for engineering timelines, we are forced to use approximations. So we'll discuss 2 different models here. This is P1 model and your FVDOI model. So P1 model, we just saw that the full RTE is computationally quite brutal because it depends on precise angles. The P1 model essentially becomes the first strategy here. It is based on a theory that sort of spherical harmonic method, where we don't let, essentially this is a method of averaging. We don't let things go transient, so to speak. Looking at this orange sphere right here, this is representing isotropic sort of assumption. P1 model assumes that radiation intensity is nearly uniform in all directions, assuming that radiation is fuzzy rather than sharp. This is perfect for inside like a dense fire or a soot cloud, where light bounces so many times that it loses its original direction, making light spread in a spherical sort of a fashion here. By making this assumption, we can actually integrate the directional intensity over all the solid angles. Instead of solving for directional intensity, we solve for a single scalar value, incident radiation G. So the payoff essentially is this equation that we get on the right here. Now, if you recognize this structure, this looks very close to what heat conduction equation is. So complex radiation problem turns into a simple sort of elliptic diffusion equation. So How well does the P1 model work? Coming to the pros at least, if you need fast results, P1 is your best friend. Its primary advantage is speed itself because it collapses physics into a single scalar equation. It adds very little overhead to your simulation. CPU cost is quite low. It is also quite robust regarding mesh. So we call this mesh independence, where it works efficiently on messy, arbitrary, unstructured polyhedral meshes, which is what you will probably use in your complex geometries. And ultimately, it is stable as well in terms of convergence, because P1 typically reaches the solution in like 25 to 30% of time required compared to FV-DOM. But it is not without its own limitations here, because speed comes at a cost. Your direction blindness is a huge factor. P1 assumes radiation is isotropic. It cannot model sharp beams. If you have laser, spotlight, or a strong solar loading, P1 will essentially fail to capture that. It also suffers from gradient smoothing, which is mathematical diffusion that we just introduced. It acts like a blur filter. It smears out sharp heat flux peaks, which can be dangerous if you're looking for specific hotspots on a wall. One of the biggest failures here is thin media failure. The idea essentially is, in optically thin media like your clear air, radiation travels in straight lines, but P1 essentially forces this into a diffusion pattern, leading to significant errors. And ultimately, P1 you can use for like large furnaces, coal boilers, heavy fires where air is thick with soot or smoke. In those environments, light scattering is quite high. That fuzzy assumption is actually correct. But for any other case where you are looking at directional sort of radiation here, P1 will actually fail. That's where FV-DOM approach essentially comes into play. So if P1 is looked at like a floodlight, the finite volume discrete ordinates method, this is collection of lasers, so to speak. It refuses to average your physics. So instead of assuming radiation as this isotropic, same in all directions method, the FV-DOM model essentially solves the transport equation for specific discrete angles. It allows us to track beams of energy exactly as they travel through the domain. So looking at the orange sphere on the right again, it represents the full field of vision, your 4 sort of phi, 4 pi, essentially the angle here from a single cell center. FV-DOM method chops this sphere into small discrete sectors represented by these arrows that we have, and this is called the S_n approximation. Each arrow represents a specific direction, specifically a direction vector that the solver tracks independently. It will calculate how much intensity is coming from or going to that specific slice of the sky. So we are no longer solving a simple diffusion equation. We are solving hyperbolic sort of transport equations for every single discrete direction. So this essentially captures the physics perfectly. It handles shadows, beams, anisotropic scattering, but it requires the solver to work sort of much harder. So to understand the cost, let's take a very simple example here. Here, standard setup is S4 quadrature. This divides sphere into enough angles to be accurate, but mathematically this means you aren't just adding one energy equation, you are adding 24 additional transport equations to your particular simulation. Coming to the pros and cons of FV-DOM itself, if P1 was sort of a workhorse, then FV-DOM is like a sniper. It's a precision instrument designed for specific high fidelity targets. Its greatest strength essentially is universal accuracy. So unlike P1, which fails in clear air, FV-DOM is valid across all optical regimes, whether the medium is optically thin, thick, or somewhere in between. Because FV-DOM tracks discrete rays, it actually captures the physics that P1 ignores. So things like shadows and beams, FV-DOM actually understands line of sight. If you place a shield between a fire and a battery cell, FV-DOM effectively calculates the shadow. It also accurately models the collimated surfaces like a laser beam or direct solar loading, etc. It also correctly models directional heat flux at the walls, ensuring that hotspots are placed exactly where geometry dictates rather than being smoothed out by the diffusion model. But it comes at a very costly price here because cost scales linearly with the number of angles. So if you run an S4 quadrature, you're solving 24 extra equations. This is a massive sort of increase in CPU time, memory usage compared to single equation model. There is also a unique risk called sort of ray effects. If you don't use enough angles, which is low resolution, simulation can actually produce artificial striping or starburst artifacts patterns, so to speak, radiating from a particular heat source. Additionally, on unstructured meshes, we need to watch for false scattering, a numerical error where mesh orientation artificially diffuses the beam. So when can we deploy the FVDOA model? Well, things like clean combustion, where there is no soot to scatter your light, or solar loading, or scenarios with complex geometries where shadows are essentially critical. These scenarios you should be using FVDOA. So far I've been talking about this concept of optical thickness as well. What is this optical thickness? So there is a dimensionless number called optical thickness. As the equation shows here, this is K times L, or absorption coefficient times length scale. This essentially is a measure of visibility, let's say. So can a photon travel your domain without hitting anything? That's the whole point here. So on the left, you have optically thin regime. This corresponds to transparent media like clear air, clean combustion, electronics cooling, etc. Here, radiation travels in straight, uninterrupted lines like a flashlight beam. So P1 model will fail in these areas because it tries to force straight beams into a diffusion cloud. And this is going to be physically wrong. So you must use FVDOA model in these particular areas where you have optically thin sort of materials. But optically thick regime, where essentially we represent opaque, dense media like inside a massive coal furnace or a room filled with smoke, etc. Here, photons cannot travel more than 1 millimeter before hitting a particle. So radiation is essentially going to scatter very quickly and much more frequently, that it effectively becomes diffusive. So this is where P1 model will work really well. It is fast, it is accurate, it will do the job. Now, there is an intermediate region as well. So as you transition closer to 1, or the optical thickness closer to 1, you should be preferring FVDOM for accuracy, primarily because you want to avoid the errors of P1 approximation, where even though visibility is low, you can still have certain cases where your photons are traveling much farther before hitting an actual obstacle. So how do we compare apples to oranges here? Let's just take a look at the first row, accuracy in thin media. This is essentially where most of the battle is going to be fought. So P1 is marked poor because the error margin is quite huge, 20 to 50%. Because it forces beams to behave like a diffusing gas, it fundamentally fails to capture the of transparent media, whereas FPDOM is quite good with error less than 5%. It tracks the rays correctly. It accuracy in clear air. If this is your goal, then P1 is simply not your option. Now, taking a look at the second row, the thick media. Well, both models are pretty good here. P1 and FVDOM are good with accuracy, 2 to 5% error. For the most part, you can still go away or get away with using P1 model. But CPU cost and memory overhead, this is where your decision will essentially come. If P1 is a baseline, then FVDOM is 3 to 10 times slower. So this is massive penalty for transient simulations that might run for days, assuming you have compressible flow, multi-component fluid with combustion, then you have conjugate heat transfer happening, and on top of that you are solving turbulence, you're solving your transient equations, and then on top of that you have to solve, let's say, just a basic S4 with 24 different equations, transport equations for just temperature. It sort of piles on top of it. So it becomes very expensive very quickly. Memory overhead, P1 solves for just one field here, incident radiation G, whereas FVDOM will require 24 plus fields, one for every angle in your S4 quadrature. So if you are limited by memory, on your cluster or on your workstation, FVDOM might crash your particular node there. Now, finally, looking at the physics type itself, P1 uses the FVM Laplacian. Mathematically, it behaves like an elliptic diffusion. It is smooth, stable, easy to converge. But FVDOM, this is FVM DIV, and it solves hyperbolic equations, hyperbolic transport. Hyperbolic equations are famously quite stiff and jumpy, so to speak, discontinuity. It is much harder to sort of stabilize, and it requires careful handling of your schemes, relaxation factors. You want to avoid divergence much more. So a very clear story here that P1 is for efficiency in dirty environments, FVDOM is precision in clear environments. Okay, one more poll we have. So for optically thin media, we choose the P1 model. What is the expected outcome? Optically thin media, this is tau sort of closer to 0. What would happen if you use P1 model there? Remember, P1 is much more diffusive, and in clear sort of media, P1 might not do well. It's not simulation will fail to converge, but much more than that, it is, simulation will run, but your result will be bad. Because P1 model cannot model sort of directional beams, and in your clear or optically thin media, P1 essentially enforces diffusion, and that's where it will essentially fail. Let's do one more. Okay. So if you decide P1 model is not accurate enough for your fire simulation, what happens if you use FVDOM model with standard S4 quadrature? What are you doing there? So you added one extra equation, you added 24 additional transport equations, you had changed the fluid density model only, or you reduced mesh requirement, making the simulation faster. Okay. So essentially the FV-DOM model, this discretizes angular space, and S4 quadrature divides your sphere into discrete directions, requiring your solver to calculate hyperbolic transport equations. And S4 essentially translates to 24 specific angles here, which is why FV-DOM is quite slower. So we essentially add 24 additional transport equations in here. Let's move from theory to syntax now. I'll primarily talk about OpenFOAM because that's where we can actually run simulations and understand radiation itself. So to activate radiation in OpenFOAM, there is a particular file in constant directory. It's called radiation properties. So as the code snippet, as you can see here, we set the radiation to on, and we define the radiation model as P1. So the most critical setting for performance is this solver frequency here. Essentially, this forces the solver to recalculate the radiation field at every fluid time step. This is recommended for initial stability, at least, especially in combustion, where temperature changes quite rapidly. Once simulation sort of stabilizes, you can increase this to 5 or 10. This means radiation is solved every 10th step or 5th step, which significantly reduces your CPU cost without sacrificing much accuracy here. There's one entry, absorption emission model. This is where you define how dirty or opaque your air essentially is. This is the optically thin thick idea here. So in this example, we're using something called the constant absorption emission. This assumes a uniform fog throughout the domain. We'll cover much more complex models like this in the upcoming slide, but the essence of boundary condition, the Marsha K condition. So P1 requires a unique boundary condition in the 0 folder. The field variable is going to be called G, incident radiation here. So in that, we do not use fixed temperature. Instead, we want to use Marsha K radiation fixed temperature. This essentially acts as a virtual window, allowing your radiative flux to diffuse into or out of the wall based on temperature difference between your wall and the fluid. So it is standard boundary condition for all sort of diffusion-based radiation models. Next, we have the FVDOM. So to enable FVDOM, you just need to change the model from P1 to FVDOM. There are going to be certain coefficients that will come into play here. We'll talk about these. Most important numbers here are n phi and n theta, as you can see on the bottom right figure here. These are essentially the azimuthal and polar angles respectively. These parameters control how finely we slice the sphere essentially. Think of these as your resolution settings, just like increasing pixels on a screen. Increasing these numbers gives a sharper sort of thermal picture, but every single slice is going to add extra cost. So the formula here, 4 times n phi times n theta, this is essentially how you will understand the total directions. So each direction requires solving a new transport equation here, and the more directions you add, more computational complexity and computational time you will essentially include on top of it. So there comes a point where by default you will always see S4 in here or 24 rays here. So why not set these numbers quite low if that is the argument? Because if you set these to a very low number, your angular resolution is going to be too low. The simulation will produce artificial sort of artifacts. Heat will look like it is shooting out in stars or stripes rather than smooth gradients. So always check for angular grid dependence. For instance, you can increase your n phi and n theta until heat flux results sort of stop changing. This is when you have enough amount of rays as well. So now let's talk about the absorption model itself. Once we have selected our solver P1 or FV-DOM, we also must define the medium itself. So we need to connect essentially the radiation to our fluid properties. In CFD, we do this by defining our absorption coefficient. This tells the solver how thick or sort of dirty the air essentially is. We have 3 different models or 3 different approaches. Option number 1, this is your constant absorption model. This is the baseline essentially, simplest approach. It assumes that your absorption coefficient is uniform everywhere and does not really change with temperature or wavelength. This is ideal for like simple tests or scenarios where medium is sort of non-participating, like your clean air in electronics cooling. You essentially need a placeholder value to stabilize your solver. Option number 2, this is gray mean. This is combustion standard, so to speak. This is weighted sum of gray gases here. Real combustion gases like CO2, H2O are quite picky. They only absorb radiation at specific wavelengths, as you can see on the jagged sort of figure here. So the weighted sum of gray sort of gases, this model here, smooths out these jagged lines into a gray average that the solver can handle efficiently. If you are simulating a fire involving hydrocarbons, this model is essential because it accounts for chemical composition of your burnt gases, and it will give you a better accuracy in terms of how your fluid is going to behave as an optically thin or thick sort of a material. And ultimately, we have the soot model. This is essentially, for cases where you have smoke or soot present inside your domain. So in a battery fire or a liquid pool fire, gas isn't going to be clear. It is going to be full of black carbon particles, and soot often dominates absorption. So this model calculates absorption based on mixture fraction or empirical sort of soot volume fraction. It adds a massive soot term to the total absorption, usually overwhelming the gas contribution itself. So equation on the bottom essentially summarizes the total effect here. So K total is equal to K gas plus C times FV times T. Essentially, this reminds us that total opacity of your fire is a sum of hot gases and solid particles. Neglecting this soot term in dirty fire simulation will underpredict your radiative heat flux. If we just take a look at one case study for today, this is the liquid pool fire here. So one of the most difficult scenarios is liquid pool fire because it forces us to deal with conflicting physics simultaneously. You have compressible flow, you have multi-component gases, you have viscosity model, density model, and on top of that you are dealing with combustion modeling, chemistry, individual species transport equations. On top of that you want to do turbulence, and along with that you also want to understand the transient nature of your fire. Then comes the part of radiation, added as cherry on top of everything here. Looking at just the diagram in the center, the flame has a sooty core. This is optically thick. Now, if we only looked at this region, we might think I can use the P1 model here really well. But as we know, edges around the fire, these are going to be much more clear air, and that is where P1 model will essentially fail. Reason again why this simulation will fail is because of radiative feedback as well, because heat will sort of radiate in all directions here, and if it is surrounded by a wall, then this heat radiation will hit the wall and perhaps it will come back to your domain itself or the fire itself. So fire only sustains itself if enough heat sort of travels back to the liquid surface to evaporate more fuel. This requires precise sort of directional heat flux as well. Now, if you run this with P1, the model acts like a blur filter. It will smear the sharp downward heat flux into a diffusive cloud. The model will underpredict sort of the energy hitting the fuel pool here on the bottom. The liquid doesn't evaporate fast enough, and your simulated fire sort of artificially dies out or grows far too slowly. But if you use FVDOM model to capture the directional heating, you will again pay for the computational cost of ray tracing essentially, or you will get the burn rate wrong if you do P1 model. Liquid pool fire essentially comes from this scenario where if you have liquid fuel poured on a particular room and it has some amount of height as well, then how quickly will that flame spread, and if the flame will be self-sustaining or not. And if it is self-sustaining, then how long will it take to burn off the entire fuel there? So this analysis becomes very necessary for your safety of enclosed spaces like labs or research centers and whatnot. Ultimately, coming to the decision matrix here of for what material to use what type of model, one of the most critical physics questions at the top here is the medium optically thin. If your answer is yes, definitely go for FVDOM, do not go for P1. As we discussed, P1 assumes radiation is diffusive. Applying it to clear air is physically wrong. You must use FVDOM to capture your directional beams here. Now, if your material is not optically thin, if it is a collimated source, which is, if your medium isn't perfectly clear, like your solar or lenses, the question here becomes, do we need sort of, okay, so question here becomes, are these collimated sources, or do you need sharp shadows as well? Like if you have a material in between and the radiation has to pierce through it or it has to reflect through it, becoming a shadow sort of. Even in these cases, you should use FVDOM because, again, P1 model is not going to be directional. It will smoothen out the intensity. It will effectively blur the thermal image here. But one of the biggest sort of questions you should be asking is if your CPU time is the critical bottleneck here, because many times getting an answer is much more important than just running your CFD to get minimal gains there. So if physics allows for flexibility, then you can go for P1. However, you should be warned that you will be getting reduced accuracy. You are going to trade precision for speed. And ultimately, if your material is optically thick like a furnace, etc., you can very easily go for the P1 model. For the most part, one pro tip or a sort of hybrid strategy that we can do is use P1 to ignite and stabilize the flow. Essentially start your simulation with the cheap P1 model to get the fluid moving, and temperature roughly will be correct. And as soon as you reach a particular stage, you can then switch to FVDOM for final data collection, where once the flow is actually stable, switch to your FVDOM for final few seconds to actually capture the precise heat flux. This gives you FVDOM accuracy for P1 speeds there. Okay, finally, best practices. In the entire webinar, we've not talked about mesh as much, but we must talk about mesh itself. Common mistake is assuming that mesh designed for fluid flow is automatically good enough for radiation. Radiation meshes often need to be different because if you use FVDOM model, for example, on a coarse grid, you will encounter false scattering. This is a numerical error where mesh essentially artificially diffuses your laser beams, making a shadow look quite blurry. So you often need a finer mesh to capture sharp shadows than you do to capture boundary layer, so to speak. Second is angular convergence. If you are paying the cost of FVDOM at all, then ensure that you are actually getting the accuracy you paid for. This is run a very simple sensitivity study. Compare a simulation using S4. This is low resolution with 24. And again, check this against S8 with higher resolution. If your heat flux results change significantly between the two runs, your initial resolution was too low. Then it comes to the point where you need to keep increasing the angles until you see this result change, essentially. And finally, never trust complex coupled equations quite blindly. Always benchmark your model. Before simulating full battery pack fire, actually simulate a simple block with a known temperature. Check this against your analytical or experimental data to ensure that whatever model you've actually used are physically realistic. And ultimately, choice of radiation model is really not just a numerical setting. It is a purely physics-based decision, which is defined by your optical thickness and ultimately the cost that you are willing to pay for your simulation itself. But don't just pick the default settings. Look at your fluid. If it is clear, if it is not clear, you let the physics essentially dictate what your solver should do. So just to reinforce a few things here, before you even open your OpenFOAM and start changing things here, please first understand, are you actually modeling normal operation, or are you actually modeling a faulty or a thermal runaway simulation? If your temperatures are sufficiently high enough, only then go for radiation, because it's a point of diminishing returns there. With respect to material emissivity, again, don't just guess. You must verify if your material is a reflector like bare aluminium, or if it is an emitter like a wrapped cell. Getting this wrong can actually significantly affect your results 10 to 20%. Solver strategy. Radiation equations are, as we saw for FVDOM model, it is quite hyperbolic. These are very stiff. They react quite violently to very small changes, hence the name stiff here. This is precisely why solver check is very, very critical. If your solver diverges or crashes, at least in the first few steps you don't need to look at boundary conditions, mesh, etc. Instead, use under relaxation. This forces the solver to take smaller steps, essentially, when updating the radiation field. This prevents your numerical oscillations. There will come a point where you will see negative temperature warnings, essentially, a common artifact in radiation modeling here. If the solver calculates that a cell is losing energy faster than it has this energy, temperature will suddenly drop below 0 Kelvin. This will cause a crash. If you do end up seeing a negative temperature problem here, check your time step, try reducing it, check your Courant number, try reducing it. And for the most part, please do check your boundary conditions. There have been instances where I myself have done it, where I think 300 Kelvin, I might put 273, or just by nature of habit, if I do Celsius versus Kelvin, I might mess up the whole thing as well. Ultimately, coming down to boundary conditions themselves, radiation sort of connects everything. Therefore, the surrounding temperature is just as important as temperature of the battery itself. If you leave the environment undefined, OpenFOAM might assume that everything is 0 Kelvin, which will just suck all the heat out of your system instantly. So define your surroundings, or at least where your battery is situated. What is this? What is the temperature there? Keep it very clear there. Ultimately, solver. This is a question that gets asked many times. How do you know you are right with validation, right? For thermal simulations, one of the biggest things you want to do is energy balance, which is, does energy in minus energy out actually equal 0? If energy is disappearing somewhere, either your mesh or your absorption model is sort of flawed. But for the most part, energy in, energy out, and checking your energy residuals, these are very important. Similarly, for a very simple case where you're trying to run for a battery failure model with convection on top of it, you could also monitor the outlet temperature of your fluid itself to really understand if the outlet temperature is being correct or not. Ultimately, you want to compare your CFD contours against like experimental or thermal camera footage at least. So especially in like a liquid pool fire case, if the shape of the flame or hotspot is essentially wrong, then radiation model will be wrong. So a visual look at what your simulation looks like compared to an experimental data or a thermal imaging itself will also really help. Great. I have final poll. So when running FPDOM model, you see heat radiating in distinct stripes or starburst. What is the root cause here? The angular resolution is too low. So again, right, if the n phi, n theta, these settings are too low, solver does not have enough sort of discrete rays to cover the entire sphere. This results in this starburst effect where heat flux appears artificially striped or star shaped there. So if a radiation simulation diverges immediately, crashing with a negative temperature, according to best practices checklist, what is the primary numerical strategy to stabilize this? Thank you very much for joining. I'll see you guys in the next one.